Hello guys, my name is Mohammad Izhaan Khan. Currently, I'm pursuing my degree in Bachelor's in Civil and Environmental Engineering from IIT Patna. So, in our today's discussion, we are going to start solving the example questions of the topic atoms from physics part. So, rather than giving you a full revision beforehand, I think that it will be better if I start solving the questions and whatever concepts are required for those questions, I give you a quick overlook through those concepts. So, in that manner, you will learn the application as well as the gist of the concept in the same time, at the same time. So, that will be better. Okay, so I'm just going to start with question number one. Okay, so the first question, taking the bore radius A naught equal to 53 picometers, the radius of Li 2 plus ion in ground state on the basis of Bohr's model will be above. So currently of the Bohr radius A naught equal to 53. To find the Li 2 plus ion on its ground state, the radius of Li 2 plus ion, see what is to be found. To find Li 2 plus radius in ground state. See, this is the question. No, the radii of the atomic orbit that is inversely proportional to atomic number that we all know already in that radius is inversely proportional to 1 upon z. So for Li2 plus, if I write, can be written as 53 in ground state with 3 picometers. So radius will be 53 upon 3 is 17.667 picometers. Any option like that? Option number C, as radius is equals to 18 picometers. That will be my answer. Next up, I have question number two. So the binding energy of an H atom, considering an electron moving around a fixed nuclei, is called it. This is the binding energy. What is binding energy? C. This is a nucleus having positive charge. This is the path of an electron. Okay, I'll say this is an electron. This is having negative charge. So there are interactions between the positive and negative charge, and the electrostatic energy can be written as A times Q1 Q2 by this distance R. Alright. So this is the binding energy. This is the binding energy. If you somehow provide the same amount of energy or an energy greater than this binding energy, let's say E. Okay. If you provide this energy, then this electron will lose its interaction with this nucleus and be gone. So this the binding energy, as its name suggests, binds the electron close to the nucleus at all. Solid. So, but if you provide an energy to an electron which will be greater than the binding energy, then obviously that electron will, surpass the energy that is binding, and it will move away from nucleus. Okay, simple. So now the binding energy of an H atom, or like considering an electron moving around the fixed nuclei, and then stated that for the nuclei you have to consider a proton, just a single positive Q charge. So the binding energy is also given to us. What is the binding energy? Minus m times E4 whole divided by 8 n square epsilon naught square that square, where m is the mass of the electron. If one decides to work in a frame of reference where the electron is at rest, the proton would be moving around it. Simple. So by similar arguments, the binding energy would be this, where m is the proton mass. Okay. This last expression is not correct because okay. So see, we'll go one by one. N would not be integral. This is what the first is. This statement is incorrect. The statement A that has been given to us is incorrect because N is integral. Alright. Statement B is Bohr quantization applies only to electrons. So this statement is also incorrect because Bohr's quantization is not only limited to electrons. Okay. So that is a myth actually, that Bohr's quantization only is secluded towards the electrons, but it is not like that. It can be further explained. Okay, but the option C, that is saying the frame in which the electron is at rest is not inertial. This is the correct answer. Okay. See, this statement is correct because in the frame of reference where the electron is at rest, the given expression will not be valid as it forms the non-inertial frame of reference. Alright. So, like whatever you expressed for the binding energy when the nucleus was at rest and the electron was at moving was in the inertial frame. Alright. But when you reverse the situation, you started looking at the electron at rest and the nucleus moving around. Then what happened was the frame was not inertial, and then you just switch the formula, so it is not like that. It would not work. So option C is the correct. So the motion of the proton would not be in circular orbits even approximately. Would not be even approximately. No, I don't think this will happen. See, proton, electron. It is moving in a circular orbit. Okay. But if you put this at rest, okay, suppose you are standing over here, then you will see that the proton is moving how? Like this. See now, you will go here, it will look like the proton is coming towards you. Then you will move further apart, the proton will look like this. Then you will see the proton from the downwards direction. And then when you will be back over here, it will look like the proton is back to its initial position. So if you stand on the electron and watch the proton, then it will also look like it is moving in a circular orbit. So option D is also incorrect. Okay. And now I'm hopping on to question number third now. Alright. So the simple Bohr model cannot be directly applied to calculate energy levels of an atom with many electrons. Okay, so question number 3 states that the simple Bohr model cannot be directly applied to calculate the energy level of an atom with many electrons. Alright, so this is the keyword, many electrons. And why is this? Yes. All the electrons not being subjected to a central force. Correct. Yeah, this statement is correct. If you ask me why, it is because the electrostatic force of attraction between electron and nucleus is a central force which provides necessary centripetal force for circular motion of electrons. For atoms with many electrons, the simple Bohr's model cannot be applied for determining the energy levels because here the electrons are not subjected to a central force. So option A is correct. Option B states so the electrons colliding with each other. It is incorrect because the electrons do not collide with each other while moving in the circular orbit of the nucleus. So the electrons colliding with each other is wrong of screening effects. Okay, but the screening effect is a major factor when you think of it theoretically, but when you calculate the energy values or numerically, the screening effect does not play an integral part or any role in it. So option C is also incorrect. The force between the nucleus and electron will no longer be given by Coulomb's law. Obviously, this is incorrect. Always the force between charged particles will be given by the Coulomb's law. Always. So option A is correct for the question number 3. Moving on, question number 4. So for the ground state, the electron in the H atom has an angular momentum h. According to the simple Bohr model, angular momentum is a vector and hence there will be infinitely many orbits with the vector pointing in all possible directions. And actually this is not true. Because, okay, so this is also a theoretical question order. So what it is saying? It is saying that the electron in the H atom has an angular momentum h. Okay, angular momentum of h. According to the simple Bohr model, angular momentum is a vector and hence there will be infinitely many orbits with the vector pointing in all possible directions electrically. This is not true. Why is it not true? Because the Bohr model gives incorrect values of angular momentum. Yeah, this statement is correct. The Bohr's second postulate states that the electron revolves around nucleus only around these orbits, for which angular momentum is an integral multiple of what? Where L is equals to N times H upon 2 pi. So this is L. Angular momentum is an integral multiple of H upon 2 pi. This is the statement of the Bohr's second postulate. Alright. So over the so and option A is correct. Why is option B incorrect? Because only one of these would have a minimum energy. No, no, no. Because in the ground state, all are in the minimum energy. As many as they can stand in the ground state, they have the same energy values. Angular momentum must be in the direction of spin of electron. No, angular momentum is not in the direction of the spin actually. Okay. It is around the movement and circular movement that the electron possesses around the nucleus. There you can use the right hand thumb rule to find the direction of the electron. Okay. So option D, because electrons go around only in horizontal orbits. No, obviously no. Why would we go around in horizontal orbits? It is diabolical. Now moving onwards, I have question number five. Okay. So question number five is stated that O2 molecule consists of two oxygen atoms in the nuclear force between the nuclei of the two atoms. Okay. So in the molecule, they're talking about in the molecular level, such as this is one molecule of O2, this is another molecule of O2, something like this or not. Let me check. O2 molecule consists of two oxygen atoms. In this molecule, nuclear force between the nuclei of the two atoms. No, they're not talking about this. They're talking about the nuclei like this. Yes. And suppose this is oxygen atom number one, and this is oxygen atom number two. So now we're talking about the interaction between these two. Alright. So let's check what they're asking. The molecule nuclear force between the nuclei of the two atoms is not important because nuclear forces are short-range. Yes, this statement is correct. The statement is correct. Why? But because nuclear force is much stronger than Coulomb's force. We already and this overcomes the Coulomb repulsive forces. Yeah. You see, there is a positive charge over here, there is a positive charge over here. This has a tendency to repel this away, this is a tendency to repel this away. We already know this. But the nuclear forces that are developed. Okay, so the nuclear forces that are developed here overcome the Coulomb repulsive forces within that. I mean, when the distance between the nucleons are very short, this happens only in that case. So if the distance is more than a few, let's say, feathermeters, the nuclear force that is generating over here at nuclear will fall rapidly as the distance is increasing. Okay, so in that case, the nucleus will start moving apart. So option A is correct in this case. Now checking for option B is important as electrostatic force for binding the two atoms. No. Incorrect because the force reduces to low value, even zero if the distance is more than a few kilometers. I have already told it. Like, see. Nuclear forces are short-range. Okay, first of all. Now, if you see there's a nucleus over here, there's a nucleus over here, they are very close. Alright, very close. So, the F nuclear will be greater than the F repulsive. This will bind it together. But as you increase the distance between the nucleus, this distance D is large. So what will happen is F nuclear will immediately start tending to zero, and there will be only F repulsion. So when there will be F repulsion, what will happen? They will start to move apart at a higher pace already. So this explains this question as well. And option number C cancels the repulsive electrostatic force between the nuclei. No, it does not cancel it. Alright. Because I already told you that nuclear force will only act when the distance will be in the range of feathermeters, very close to each other. It is not important because oxygen nucleus have equal number of neutrons and protons. I'm sorry. So this is important because the number of nucleons are not significant, but the distance between the two nucleons, that is what is important for such scenarios. So O2, and now we have question number 6. So two atoms in the ground state collide inelastically. The maximum amount by which the combined kinetic energy is reduced is I'm sorry. So two H atoms in the ground state collide inelastically. Alright. So at the ground state, lowest energy state, that is the ground state. Alright. So the electron revolving around the smallest orbit in the ground state has the radius of volts, that is A naught. A naught is the radius when an electron is moving in the ground state. Okay, ground state or the lowest energy state, it is revolving in the smallest orbit, and it will have the radius of volts. So the energy in this state is what? E1 is minus 13.6 electron volt. This is the first E1, right? So the maximum amount of kinetic energy that can be reduced when one of them goes to first excited state in inelastic collision, that will be 2 times 13.6 electron volt. There are two atoms, right? Okay. So in elastic collision, one of them goes to the first excited state and the maximum kinetic energy is reduced. So the total energy of the two H atoms after collision, that we can determine using 13.6 divided by n square. It's 13.6. Yeah. N square minus 2 square. Okay, so 4. 3.4 electron, 13.6 electron, 0.46, 14, 17 electron. Okay. So the maximum loss in the combined state will be what? Say it's 27.2 electron volt for Z and minus 17 electron volt. It will leave me with 10.2 electron volts. Okay, so it is the option number 1. 6th A. Alright, now moving forward to question number 7. Okay, so there is a set of atoms in an excited state. Okay, a set of atoms in an excited state decays in general to any of the states with lower energy. Alright, okay, so 4 options are there. Into a lower state only when excited by an external electric field. Altogether simultaneously into a lower state, so emit photons only when they collide. Okay. So I think option A is correct. A set of atoms in excited state decays in general to any of the states with lower energy. Yes, the electron in a high state will want to decay to go back into a state where the energy will be low. So option A will be correct. The electrons in the excited state will have a tendency to fall to any state which has a lower energy. Alright, so in this process, the electron emits a photon. That is what it is. No other field of collision is needed for this transition or for emission of photons. This you have to remember. See, I see this is an energy higher, this is an energy lower. So what will happen? Electron will be in an excited state over here, but it will finally come back down to an lower energy state, and in this process, it will emit a photon. Okay. Moving forward, we have MCQ type of questions. So question number 8. An ionized hydrogen molecule consists of an electron and 2 protons. Alright. So the protons are separated by a small distance of the order of angstrom in the ground state. The electron will not move in circular orbit. The energy would be 2 raised to the power of 4 times of that of H atom. The electron's orbit should go around the proton. The molecule will soon decay into a proton and a H atom. Okay, so let us check. So in option 8 is given the electron would not move in circular orbit. This statement is correct. See, an ionized H molecule consists of an electron and two protons. Okay, the protons are situated at a small distance of the order of angstrom from the ground state. The electron would not move in circular orbit. Option is correct. Okay, why is it correct? Because the hydrogen molecule that is there, it contains two electrons and two protons. But ionized hydrogen molecule that will contain only one electron and two protons. See, a normal hydrogen atom, what will it have? It will have two protons and two electrons. Suppose it gets excited. So in this case, the hydrogen atom will have two protons but only one electron. Anyway, simple. So in the hydrogen molecule, the two nuclei of the two H atoms are separated by distance in order of angstrom. So this indicates that nuclear forces will be present. The nuclear forces that I was talking about in the range of angstrom, that will be there. F nuclear. So nuclear forces will be acting over it. So the electron no longer moves in circular orbit. So the option A is correct, first of all. Now, option B, the energy would be 2 raised to the power of 4 times that of an H atom. No, this is wrong. The energy will not, by the factor of 2 raised to the power of 4 is wrong. Okay. There will be a factor, but it will not be 2 raised to the power of 4. So the electrons orbit would go around the protons. Electrons orbits would go around the proton. This statement is also correct. Why? Because the hydrogen molecule contains two electrons and two protons in the initial state that already discussed with you. In the excited state, it will have only one electron. So in the H molecule, the two nuclei of the two H atoms will have that force nuclear between them. So the nuclear forces will cause the same thing that it was doing earlier. It will make the electrons orbit go around the protons due to the force of electrostatic. Option B, the molecules will soon decay into a proton and the H atom. No, this is not correct. Nuclear forces will be present and the molecule will not decay. So the correct options in this case were A, 3, the correct options were A and C. So now next up, we have question number 9. Just give me 1 minute. So next up, we have question number 9. So what has been given to us? We have to consider aiming a beam of free electrons towards free protons. When the scattered electron in the proton cannot combine to produce an H atom. Okay, so why is this occurring? That is what they're asking me. So consider aiming a beam of free electrons towards free protons when the scattered electron in the proton cannot combine to produce an H atom. Energy conservation, obviously true. So option A is correct first of all. Because when a beam of free electrons are aimed, the electrons scatter on the count of energy conservation. See, to make an H atom, they have to be provided by some energy that will be equal to the or greater to the binding energy. Right? Because the electron and proton are getting bounded together in this case. Yeah. Without simultaneously releasing energy in the form of radiation. This is option B. This statement is also correct because if an electron and proton do combine to form hydrogen atom, a large amount of energy will be produced, which will be released in the form of radiation. Because of momentum conservation, no, does not play any role in this combination, right? Momentum will be conserved, I agree, but it will not play any role. Because of angular momentum conservation, same thing goes for angular momentum also. It will be conserved, I agree, but it will not play an impactful role or any role in this combination that we are talking about. Alright. Option D is also incorrect. The correct option for this part was option A and option B. Yes, so in the 9th, the correct option or option as well as option B. So now, next step, we have to check for question number 10. The Bohr model for the spectra of an H atom. will be applicable to hydrogen in the molecular form. The option number one will not be applicable as it is for a helium atom. Okay, so it's valid only at room temperature. Predicts continuous as well as discrete spectral lines. Okay, so let's check again. Mhm. Will not be applicable to hydrogen in the molecular form. The statement is correct because, as Neil Bohr's, it is Neil Bohr's theory, right? It proposed that the atomic model for hydrogen and hydrogen-like atoms, it is different. Alright. He did name it something, but I can't recall it right now. But hydrogen and hydrogen-like atoms will be treated differently. This was the theory of Neil Bohr. So, what are hydrogen-like atoms? In which they have a single electron atom. In the molecular form of hydrogen, it is not a single electron system. So that is why option A is correct. Check it. As Bohr stated that the Bohr's model for the spectra of H atom, okay, will not be the same for hydrogen and H-like atoms. What is so unique about them? They have only one electron in their only hydrogen का molecular formula is this. Okay, if I write something about helium, it is He2 4. So it has, excuse me, two proton, two neutron. But in case I write about helium positive, it will be one electron, two proton, two neutron. So this is also hydrogen-like. So what is unique about them is one electron that they have. Okay. So, but if you see about hydrogen, H11, H11, it is having two electrons. So this Bohr model spectra for H atom will not be applicable for H2 because it is not hydrogen. It is having two electrons. Okay. So option A is correct. Option B will not be applicable as it is for a helium atom. This statement is also correct due to the same reason. Because in the helium atom, I told you H2 4, the number of electrons is 2. And what we are talking about is one electron system. So the helium part is also correct. Now option C, it's valid only at room temperature. It has nothing to do with temperature, so it is incorrect. Okay. It is continuous as well as discrete spectral lines. No, it is not correct. Alright, so the correct option for question number 10 will be what? A and B. A, B. Now we will on with question number 11. The Balmer series for the hydrogen atom can be conserved if you measure the frequencies of light emitted when an excited atom falls to the ground state. Okay. The Balmer series for the hydrogen atom can be conserved if you measure the frequencies of light emitted when an excited atom falls to the ground state. This statement is incorrect because the various lines in atomic spectra are produced when electron jumps from a higher energy state to the lower energy state. Okay, so to observe the Balmer series, the electron should jump to the first excited state directly. So that means the option number 1 incorrect. Now option B. If you measure the frequencies of light emitted due to transition between excited state and the first excited state, yes, this is true. This statement is correct because the Balmer series can be observed only when the light is emitted due to the transition between higher energy state to the directly the first excited state. So option B is correct. Option number C is in any transition in an H atom. Okay, any transition in an H atom. No, this is not correct. No. So D is a sequence of frequencies with the higher frequencies getting closely packed. And as a sequence of frequencies with the higher frequencies getting closely packed. This statement is correct. This statement is correct. So correct options are option number B and D for this. Option B. So it's option D. Moving forward to question number 12. So we have been given the energy, let En be. En can be determined for the point 8 epsilon naught square, then E raised to the power of 4 n squared h squared. So with the energy of the nth level of H atom. So if all the H atoms are in the ground state and radiation of frequency E2 minus E1 by falls on it. So we have four options there. And state of frequency E1 minus E2 by H, it will not be absorbed at all. So the radiation of frequency will be what? Radiation of frequency. Radiation has a frequency of E2 minus E1 whole divided by H. So which, because E is equals to H nu, so if you want to calculate nu, it will be E upon H times this will be E2 minus E1, because it is changing its state as it is given in the question itself. So this is the frequency which indicates that the energy of the radiation will be E2 minus E1. So this is sufficient for absorption. Okay, in the first excited state, this energy can be absorbed, this frequency absorbed can be absorbed. So it is sufficient. So option A is incorrect. This statement is some of the atoms will move to the first excited state. So it is the correct option because the radiation, as I told you, has a frequency. So it is sufficiently large for the electrons to be pushed from that first to be pushed to the first excited state. So option B is correct as of now. Now option C, all atoms will be excited to the n equal to 2 state. We cannot say this because there will be some loss of energy. Alright. And option D, no atoms will make a transition to the n equal to 3 state. We'll be short on energy. To make a transition to n equal to 3, we only have E2 minus E1 energy and that will be short. So option D is also correct. Option D is also correct. Yeah. So the correct option are B and D for this one. Moving onwards to question number 12. Okay, so this was question number 12. So now we have question number 13. A simple Bohr model is not applicable to helium-4 atom because helium-4I is an inert gas. Helium-4 is an inert gas. Helium-4 has neutrons in the nucleus. Helium-4 has one more electron. Electrons are not subject to central forces. So first option, which is an inert gas, that is incorrect because the inertness is the nature of the molecules, alright. So it does not describe how the atoms behave. It is also the inertness tells us about what can be the possible arrangement of the electrons in the shells of the atom, but it does not have to do anything with the model of Bohr that it suggested. So option A is incorrect. Moving on to option B. Helium-4 has neutrons in the nucleus. Yes, this statement is true. The reason is it will have two electron system, right? Helium-4 will have two electron system and we want what? We only want one electron. So option B is correct as of now. Okay. Helium-4 has one more electron. Correct. Two electrons, two protons, two neutrons. What do we need? We need one electron. What is it here? Two electrons. So it has one more electron. Okay. Number D. Electrons are not subject to central forces. Yes, this statement is also true. See, let me write something for you over here to prove option D correct. The statement is correct because for one electron system, electronic energy is sum of its kinetic as well as potential energy. So if I can write it as this kinetic plus E potential. For two electron system, there is an additional potential energy that can be put in over here from the interaction between the two electrons also. So E n is equals to E kinetic plus E potential plus I can write it as E P1 minus 2, so E again. Okay, so therefore for two electron system, electrons are not subjected to a central force like in the one electron system. That is the case over here. So that is why option D will be correct. So correct will be option C and option B. And also option B, B, C, D. Moving on to these very short answer types. Okay, so let's see. See, the first question is the mass of a hydrogen atom is less than the sum of the masses of proton and electron. Why is this? Okay. So what has been given to you? There's a hydrogen atom is there, an H atom, which consists of one electron, one proton, one electron. And the mass of this H atom, H ka mass of H mass is less than the sum of the masses of electron as well as the proton. So, according to Einstein, what he stated that mass is just another form of energy and can convert this mass energy. What was the relation? Energy can be written as mass times c plus square. So this means that mass is just another form of energy. So in this case, we can say that there is a mass defect which can be determined. So basically, the concept over here is C. If I say that the mass of electron is 1 kg, the mass of proton is also 1 kg, and it is making hydrogen atom. But the H atom has a mass of 1.5 kg. So it should have been 2 kg, but it is 1.5 kg. So there is some mass defect, right? That is written as delta M. Now, what is this mass defect? What should have been 2 minus what actually is 1.5, 0.5 kg. So how much energy has been generated due to this mass defect? Delta MC square will be 0.5 kg into c square. That is be 9 into 10 to the power 3 to 10 to the power of 8, so 10 to the power of 16 joules of energy just due to a half kg mass defect. See the energy which is generated. It will be approximately 4.5 into 10 to the power of 16 joules of energy. So much. Just due to half kg. So yeah, so now let's start the solution for this. Yes, I just wanted to tell you about what is the mass defect. So the solution will be the hydrogen atom can be denoted by this. So there's one electron and one proton we already. So number of protons is equal to 1, number of electrons is also equal to 1. Okay, but the mass of H atom will be, let's see, M hydrogen M. So it is not equal to the sum of Np plus Ne. Alright, now I can write delta M. Delta M will be what? Np plus Ne minus N hydrogen. Alright, now the E binding that it will generate will be equal to this delta M times C square. So delta M I can write as E binding upon C square. So with delta M, if I want to write it correctly now, it will be Z times mass of proton plus A minus Z times mass of neutron. Okay, minus this M. Alright. So the mass will become mass of hydrogen is equals to mass of electron plus mass of proton minus delta M. And if I want to write it, mass hydrogen will be equal to mass of electron plus mass of proton minus binding energy divided by C square. So the quantity Kb upon C square will be greater than 0. So therefore, mass of hydrogen will be always less than mass of electron plus mass of proton as we have proved. Okay. So we have answered the question number 14 right now. Moving on to question number 15. Imagine removing one electron from helium-4 and helium-3. Alright, so their energy levels, as worked out on the basis of the Bohr model, will be very close. We should explain why. So we know that Niels Bohr proposed a model for hydrogen atoms and hydrogen-like atoms which are single electron. So in order to explain stability of atoms, that was the main agenda behind this. So this model is applicable to helium-4 and helium-3 after removing one electron from each. That will get them in one electron state. If you remove one electron from both of these atoms, you will get them one electron state. So that is what you want. Alright. So on removal of one electron from both of these, both atoms will have electron as in each atom. Correct. And the nucleus will be much heavier than each atom. So stability can remain, and these atoms are very close to H. So the energy level are as of hydrogen atom, and these atoms will be very close. After removing one electron from each, they become hydrogen-like single electron atoms. See, this is a hydrogen atom. Right? It has one proton, no neutron, one electron. Now I'm going for helium-4 being helium helium-4 having two proton, two neutron, two electron, one electron, two proton, two neutron. Okay, so it is also hydrogen. So at center, it has a bigger and more powerful nucleus with two positive charge, 2p, and mass is also treated two neutron. Okay, and there is only one electron. Okay, so what is happening over here? Always remember that how many electrons are if the electrons around the nucleus are more, these electrons will have entire electron repulsion between them, which will cause this electron system to be widely spread around the nucleus. Okay, and if it will be far from the nucleus, then the force that it is acting, that the force it is pulling the electron, the nucleus is pulling the electron, will weaken because the force is inversely proportional to the distance cut square. So if there are many electrons around the nucleus, then due to electronic repulsion, they start to move away from the nucleus and away from each other as well, away from each other, and this will cause being moved away from the nucleus as well. This is what I should see. And when this happens, it will weaken the electrostatic pull that the nucleus is putting on the electron. Okay, so but in this case, as you can see, the nucleus has a charge of plus 2q, and there must have been two electrons. Okay, and these electrons would have repelled themselves, and they would have made a certain distance away from each other. But now, since there is only one electron, there is no anti-electron repulsion. But there is a very strong electrostatic pull that the nucleus is having on the electron. So it is having just what Bohr had said. It is just exaggerating the same things. It is acting like a hydrogen-like atom with a more powerful nucleus. Moving onwards to question number 16. When an electron falls from a higher energy to a lower energy level, the difference in the energies appear in the form of electromagnetic radiation. Why cannot it be emitted in any other form of energy? Okay, it is also a good question. See, what is the question is saying? The question is saying that when an electron falls from a higher energy to a lower energy, okay, so the difference in their energy, whatever it is, say En minus En, M is the other energy state I'm saying. So this energy will always appear in the electromagnetic radiation form, but why cannot be it emitted as any other form of energy? This is what the question is asking. So you can answer it in such way that an accelerated electron produces electric as well as magnetic field. Therefore, electronic interactions will always be only electromagnetic. So the energy which it is getting will be electromagnetic energy. Therefore, the transition of electron from a higher energy to a lower energy, the difference in energy will always occur in the electromagnetic radiation form. See, I am repeating myself again. An electron that is accelerated, it will produce electric as well as magnetic field. Therefore, electronic interaction is always only electromagnetic. Alright. Hence, the energy is in the form of electromagnetic energy. Therefore, when the transition of electron from a higher energy to a lower energy level is occurring, the difference in the energy appears in the form of electromagnetic radiation. All right. Moving on to question number 17. With the Bohr formula for the hydrogen atom unchanged, the proton has a charge plus 4 by 3 electron and electron has a charge minus 3 by 4 electron. Okay. So the charge of proton, right? Charge of proton Q2 is plus 4 by 2 and charge of electron is minus 3 by 4. Bohr's formula requires the product of the charges should remain constant for given value of charges. So Niels Bohr's formula for electron moving around a stable nucleus, it had to be computed with the centripetal force. So the electrostatic force of attraction is what? Force is equal to 1 upon 4 by epsilon naught. Q1 Q2 by R square. So Q1 Q2 by R square. Okay. And the centripetal force was equals to mv square by R. Okay. So since F is directly proportional to the product of Q1 and Q2, if I say that my Q proton has a charge E and Q electron has a charge of minus E, then the force will be equal to some constant C times minus E square. And the case that has been given to us, if we do it for it, like QP is equals to plus 4E by 3 and QE is equals to minus 3E by 4. If we try to find the force due to this, it will be proportional, and to remove the proportionality, I have used a constant C. And I just multiply 4 for 3 minus E square. Okay. So, same. So since it is same, we can say that the force is under normal condition and there will be no change on it. The formula will be unchanged. Now question number 18. To consider two different hydrogen atoms, the electron in each atom is in an excited state. So is it possible for the electrons to have different energies but the same orbital angular momentum according to the Bohr model? Okay, so this is the question. So you have two different hydrogen atoms. The electron in each is in an excited state. According to Bohr's postulate, the electrons revolve around the nucleus only in the orbits which have angular momentum L as an integral multiple of h upon 2 pi. Okay, so h is the Planck's constant over here, if you know. So according to Bohr's model, electrons having different energy level will have different values for n. Okay, so n is then proportional to n. So the electron having different energies will be a different energy level. They will have different values of n, hence different values of angular momentum L. Hence, it is not possible for the electron to have different energy but the same angular momentum according to the Bohr model. See, being different energy state, if you have different values for n, and if you have different values for n, then you will have different values for l also. Alright. So being in the same orbit, you cannot have different values of angular momentum because the n will be constant now. You cannot have different values for angular momentum. So this is not possible, as I've already told you. Now question number 19, short answer type question. So positronium is just like hydrogen atom with the proton placed by the positively charged antiparticle of the electron. Okay, what would be the ground state energy of positronium? Positronium is just like a hydrogen atom with the proton replaced by positively charged antiparticle of the electron called the positron, which is massive as the electron. What would be the ground state energy of positronium? Positronium के बारे में बिल्कुल. So first of all, I would like to write the energy En, which is by minus Ne4 upon 8 n square epsilon naught whole square by x square. Okay. So n is reduced mass of electron, mass of proton. This all you already know. So the reduced mass n I can write as 1 upon n equals to 1 upon m1. For the system of masses m1 and m2, I can write it like this. So the reduced mass for positronium whatever I'm getting over here, I'm just putting in the value for it, n electron plus 1 upon n e. Okay, so subscription, it will be 2 times n. So the mass n, which will come out to be will be n by 2. So n is the mass of electron, therefore energy of positonium atom is determined as, if I want to write it, energy of the positonium atom En minus n e 4 8 n square epsilon naught square square and by 2 e 4 En dash will be equal to minus 1 upon 2 into 13.6 electron volt. En dash will be minus 6.8 electron volt. So the energy will be minus 6.8 electron volt. The ground state energy of positonium. Positonium ground state energy will be minus 6.8 electron volts. So, okay, so I think we should end our session till here today. And in the next session, we'll start a question from question number 20th. All right. Now, how many questions are there? 29. So, bye bye. Thank you for your time.